I think some students are still not in the room. Yeah. Okay. Some of you have asked me questions about the calculation of the volume flow rate, mass flux, or mass flow rate. The first thing you need to keep in mind is, okay, let's say the definition. Okay. The first thing you need to keep in mind is we calculate the volume of fluid per unit time across any section. So it's actually time rate. That's why we here specify its volume flow rate, okay? Because volume flow rate across a section. So if we take an element area, just like here, we take element area for this cross section, okay? We take the element area and then we know the volume of fluid flowing per unit time across this element area will be V dot N dA. We have explained, oh, sorry, I forgot to record. Okay, I need to record. Okay, I have explained what this means, right? dA is actually the area of the differential element, and N actually indicate its normal direction. The normal direction is defined to be always go forward, go outward, sorry. Is always should be outward, just like here. And so we know in delta t time period, the volume, the fluid volume flowing across this differential element will be V d delta t dot NDA, right? Because we calculate the volume, right? Calculate the volume will be the length delta t, or the distance the fluid traveled during delta t period will be V delta t. So the fluid volume flowing across this section for this time period will be can be calculated, right? So this will be the area of this differential element, because the velocity sometimes is not perpendicular to the normal direction of this differential element. So only the component, right? Only the component along the normal direction will go out of the section, right? Because for this velocity, with this vector, we have the two projection, two components. So one is Vn, one is Vt, tangential component of velocity. That's for sure that for this component, the tangential component of the velocity will not contribute to the fluid volume flowing across this differential element. So that's why here we use dot product, because we know the dot product for two vectors means the magnitude of the two vector. Let's recall what we have learned in theoretical mechanics. A dot B means the magnitude of A and B times the angle between the two vectors, right? So that's why here M, and this is the fluid volume flowing across the differential element during delta t. And because we need to find out per unit time, so that means we need to divide by delta t. So cancel out. That's why we got finally we got this v dot nda. We said sometimes you can write down this way. Yeah, it's the same. Okay. This one indicate to represent the volume flow rate across this differential element. So for the total volume flow rate, we should integrate over the area of this cross section, right? Just like here or just like this one. So we need to take the integration over the total area. That's why here. So we have explained, we have solved this problem together. We know the velocity distribution for this fluid. This is a free surface. This is solid boundary. Okay, this is solid boundary. And the velocity, if we establish xy coordinates, x coordinates is along the solid boundary, and y coordinates is perpendicular to the solid boundary. If we want to find out the volume flow weight per unit weight of this cross section, I mean, this cross section, I need to specify this. So we need to find out volume flow weight per unit weight of this, just like the waiver of the waiver section. Okay. So we need to find out we need to find out the flow weight, volume flow weight, and the mass flow weight for this flow wave for this waiver. And unit weight means here we just saw 2D is a plane flow, but actually we know for any waiver is actually 3D. And so we got Z direction, okay. So this is XY, this is XY in this plane XY. We also got the direction or the coordinates. We mean in the coordinates, it's just unit width or they equal to 1. We have done this before in fluid statics. We said this is just like a straight plane, and this is a straight plane, and we need to calculate the pressure force on this straight plane per unit weight. So here it's the same. So we need to calculate the volume flow weight for this cross section is unit width. So just like what we have defined, we have given the definition of the volume flow weight. First, we take the element, differential element. This differential element and the area should equal to dy times 1, right? Because it's unit weight, right? Delta H. Sorry, I can't understand you. You should be written in English, okay? So this is dy, right? And so according to the definition, volume flow rate, for example, so will be V dot dA, right? And V dot dA here, because the velocity is perpendicular to the differential element area, so it will equal to, this will be A, okay? So here should be V dA, right? And the velocity is given. So we just write down the velocity here. dA is actually equal to dH times 1, right? So here, this is for the differential element, the volume flow rate. For the total cross section, for this one, okay, I need to specify here, cross section. So for the integration, the lower limit should start from 0 because from the y coordinates 0, and this point for the lower limit corresponding to the point located on the solid boundary. The other will be located on the free surface. So y equal to 0 lower limit, and the upper limit should be h. And because it's unit weights, so u dh, sorry, u dh times 1, just like here, okay? Oh, sorry, it's not dh. Should be dy. You're right. You just correct me. So here, because for this potential element, this should be dy. Okay, this should be dy for this differential element should be dy. Yeah, you are right. Okay, so here this will be u. This will be u times dy. Actually, we times 1 unit weights, and then we integrate for the whole cross section and limit, upper limit. Okay, that's it. Any question about this? Very good. You ask me questions. That means you just have really look into the problem. That's very good. Okay, so today we will introduce the definition of system and control volume. We should you see the flow classification, steady and unsteady, 1D, 2D, 3D flow, and laminar turbulent flow. Okay, so uniform, non-uniform flow. Very important here for the gradually varying flow and rapidly varying flow. For the gradually varying flow, that means streamlines are almost parallel to each other. That's streamline. That's gradually varying flow. Okay. So today we continue to introduce the difference between Lagrange and Unarian view, because we know that in mechanics we have two different point of view. One is Lagrange to follow through the particle. The other is Unarian, is to focus on space point. That's for differential, right? But if we have a collections of fluid particle or a collections of space points, so what will it be? So system is actually arbitrary quantity of mass of fixed identified. Or we can say system is actually a collection of fluid particles. And everything external to this system is denoted by the term surroundings. And the system is separated from its surroundings by its boundary through which no mass occurs. So system is a collection of fluid particles, and system is separated from the surrounding by its boundary. And across system boundary, there will be no mass go out and all go in. On the contrary, is control volume. Control volume is actually a collection of space points. All we just is just a specific region, is a geometrical region. For the control volume, it got open boundaries because through the boundaries, I mean, to isolate the country volume from the environment, the boundary, through the boundary, mass, momentum, and energy are allowed to occur is unary point. What does it mean? Just like here, we have the purple line and the green line, we have 1122 to indicate the boundary. For 1122 at T moment, all the particles inside 1122, it can make up a system. And then as with the time flowing, the boundary of this system, of the original system 1122, will become one star, two star. But the inside the system, the particles remains the same. They will not change with time. Okay. So for the system, there will be no mice can occur its boundary. Sure, for a system, it may interact with its surroundings by transfer of heat, transfer of moment, transfer of energy. And for the system, its boundary will continuously change size and shape, but it always contains the same mass. Why? Because it always contains the same fluid particles. Just for example, your classmates, we just for your classmates can represent fluid particles, all right? So if we say your class the students formed a system, and then no matter where you go, you are inside the system. But because you are walking, and the system boundary may change size, may change shape. Okay, just like here, even the solid the boundary for the system did not change shape, did not change size shape, but it will go in down with going downstream with because the fluid flowing. This system, obviously, system is for Lagrange view. Okay, and in contrast, control volume, just like here, at time moment t, its boundary is 1122. For this region, we just define this is a control volume. So at time t moment, inside this control volume 1122, there will be some particles. For example, particles A, B, C, D, E, F, just thousands of them, thousands of blood particles there. And the fluid going downstream, and definitely some fluid particles inside the country volume 1122 will go out of the country volume. And at the same time, some fluid particles will go in, will flow into the control volume through its boundary right. For the control volume, the boundary of the control volume is defined as control surface. We use CS to define the boundary of the control volume. Okay, so here from this dot flow, it's very obvious for system collection of fluid particles, and the mass of the system is always conserved because the system always consists of the same particles. There will be no mass transfer through the system boundary, but the boundary of the system may change with time. For the control volume, here it's a fixed control volume. That means the region is fixed, okay? Just here, 1122, or we say at the time moment, the boundary of the system and the control volume we choose are coincident with each other. But as flow going downstream, the boundary of the control volume 1122 is still fixed. It will not change. It fixed. It just stay here. Okay, it's just a geometric shape. But as the flow going downstream, the fluid flowing, some particles go into the control volume through its control surface 1 and other fluid particles inside the control volume and will go out of the control volume through its boundary or its control surface 2 because this is duct. We say solid boundary. We know that for the boundary or the control surface 1 2 there will be no flow can across the solid boundary. Okay, so that means flow can only go in or out of the control volume through its control surface 1 and 2. Okay, so in summary, repeat it again and again. Okay, system is a collection of metal fixed particles. Control volume is a volume space through which fluid can flow. Sure, we can kind of fix control volume. We can got moving control volume, and it can even can deform the control volume, just like when you blowing balloon. The boundary or the shape of the balloon, we can regard it as a CV, a control volume, and sure, definitely the shape of the control volume deform, right? So that's in control volume, but we will not study deforming control volume, okay, for us in this course. Here, you say we have introduced the definition of system and control volume. The relationship between a system and a control volume is quite similar to the relationship between the Lagrange and Unary flow description. In the system or Lagrange description, we follow the fluid and observe its behavior right as it moves about. However, in the control volume or Unary description, we remain stationary and observe the fluid's behavior at a fixed or at a fixed region. Okay, so for the control volume, just like the system you choose in thermal mechanics is very important. You can choose control volume as you wish, but different choice will sometimes solve problems will depend on the choice of your control volume, whether it's easy or difficult. Okay, here we give some example of the control volume. So this is a pipe. This is a pipe flow. Inside the pipe flow, we can choose the boundary here, the boundary of the control volume. Okay, so it's cross section. It's two cross section plus its circumferential section, and it's made up control volume. So here for the jet ranging, and we can choose the blue dashed line to be a control volume. Okay, this is our rectangular control volume. To inside the control volume, we got the flow, and we got also, this is all air and the jet engine. Okay, this control volume moving with the jet engine. This is a moving control volume. Sure, just as we said, when flow can be steady or unsteady, it depends on the reference frame. Here also, if you choose this control volume when you observe on the Earth, this is a moving control volume. But if you stay on this jet engine and move with this control volume, this will be a fixed control volume. And for this blue, we just take the boundary of the blue as the control volume. So this control volume is a deforming control volume. Here, you always need to remind yourself control volume is just a geometrical definition. It's just a region you are interested in and you can choose by yourself. Okay. So in thermometric mechanics, we have a lot of basic law applied to a system, right? We have the equilibrium equations. We have Newton's second law. We have mass conservation for a system. But that all apply to a system. However, we will know that for a system, just for example, we got fluid property for this sum inside this sum as phi, and we can take the time derivative of this fluid property. For example, the easy one, the mass of the system. Here, this is a phi integration tank, and then at t equal to 0 moment or at the initial time, we take the boundary of the extinguisher tank, say the blue dashed line at the boundary for the system and for the control volume. That means at the initial time, the boundary or the region of the system and control volume are coincident, are consistent with each other. So at the initial time, the fluid inside the system and inside the control volume will be the same, right? But if you have tried to use the phi integration, so when t is not zero, some of the fluid will go out of the extinguisher. You say for the system, we mean for the fluid particles collections, some still stay inside the tank, but some out of the tank. That's why here we use the green to indicate the system. So for the system, some inside the tank, some out of the tank. The boundary of the system, the shape, the size, both change, right? But for the system, its mass, its total mass will be conserved. So for this one, it will equal to 0. It's very important we know that mass is conserved, right? So for a fluid particle, mass is conserved. For a collection of fluid particle for fluid groups, particle groups, the for fluid particle system, the mass is also conserved. It will not change with time. So the time weight is equal to 0. Only its boundary shape and boundary size changed. However, for the control volume, the mass inside the control volume will be different from its nature moment. Why? Because for the control volume, here it's a fixed control volume. At the initial moment, the fluid is whole the total fluid is inside the tank, right? This is M. And after you have used the extinguisher inside the tank, some inside tank, some out tank. So in the control volume, inside the control volume, the mass, well, the mass actually decreased, right? So for the change of mass inside the control volume, the time rate, well, smaller than zero will be negative, right? Because the mass inside the control volume decreased because some go out of the control volume through its control surface. Control surface is actually the boundary for the control volume, or the boundary is actually is to isolate the control volume from its surroundings. Okay, so we should know what its control volume, what is control surface. So here, instead of the extinguisher, you can use the perfume can, the spray can. Okay, so it's the same for the system because even its shape and size changed after using, but some out of the can, some inside the can, but the system still consists all the perfumes. So its mass change rate with time should be equal to zero. However, for the control will be zero for the system. However, for the control volume, and at the initial moment, you got the whole tank of the perfume. But after using, you just got less perfume inside the tank, right? Inside the CV. So that means the mass inside the CV decrease, and so the change of the rate of the mass will be smaller than zero or will be negative. Here, you know what that means, right? Here, this is the volume for the differential element. And then times the density will be the mass for the differential element. And then you integrate over the whole volume will be the total mass of the control volume. Okay. Here, the same, this will be the volume for the differential element times density will be the mass for the differential volume, and then integrate over the whole system. It will be the total mass of the system. Okay. Just now we said we can choose control volume as your wish is just a region, right? It is just a region you would like to observe. However, the selection of an appropriate control volume in fluid mechanics is very, very similar to the selection of an appropriate free body diagram in theoretic mechanics. It's very important. Okay, so we know in theoretic mechanics we can choose different objects to draw FBD and then write down the equilibrium equation or dynamic equation. So different choice will result in different you say easy or difficult. Okay. Solution of a typical problem will involve determining parameters such as velocity, pressure, and force at some point in the fluid. Generally speaking, usually it will be good to ensure that this point is located on the control surface. We know control surface is actually the boundary of the control volume, not buried within the control volume. Okay, so The unknown, the values we want to find out will then appear in the convective term. Convective term, do you remember what means convective term? We have introduced, we have talked about material derivative or mass derivative or total derivative, right? Total derivative for a fluid particles value is actually equal to the local derivative plus convective derivative, right? Because the fluid moves, so its value will change because it's motion, because we use Unarian view, we just record what happened for fixed space points, right, in hydraulics or in fluid mechanics. So this is convective terms, okay. So for example, here for pipe flow, if we want to calculate the velocity or the pressure at point one, it will be good that you choose the control volume this way. This is a rectangular control volume. Why we choose rectangular control volume? Because its control surface is easy to calculate, right? So it's better that the point one is located at the control surface. Okay. Yeah, if you choose this way, even it's still a rectangular control volume, but the point one is buried inside the control volume, so the value of the pressure at the point one will not appear in the equations. What happened inside the control volume one maybe can be explored. So so it's not good. Sure, definitely you can also choose control volume in this way, just like figure C. Point one is still located on the control surface, but the control surface is not perpendicular to the velocity. So this one, yeah, works, but it will be more difficult. Why? For example, if you want to calculate the volume flow rate across this control surface, sorry, if you want to calculate the volume flow rate across the control surface AB, and then you say we have V dot dA, right? So it's not perpendicular. So you need to times the cosine of the angle between the velocity and the cross section AB. So in mathematics, it will be more difficult. Okay. So after we have learned the definition about system and control volume, let's study very important equation, continuity equation. Actually, this is for mass conservation. We just call it continuity equation because mass is continuous. Okay. We consider a cubic element oriented so that its size are parallel to the XYZ axis. We just assume it's incompressible flow. So this is a cubic fluid element, and we can calculate the mass flow rate or the mass flux per unit site, per unit, per control surface. Because for this control volume, for the element for this control volume, we will have 6 control surface, right? Left and right side, up and down side, front and back side. We have 6 control surface. So for the left plane, left side, we can calculate its mass flux. So the mass flux rate per unit area will be density times x velocity times 1, right? It's per unit area. So this, because we know because here, sorry, this is dz, this is dx. this is dy, okay? And so u is actually perpendicular to the left side, and the x velocity will contribute to the flow flux, but the y velocity and z velocity will not have no contribution, right? So the u times the area will be the volume flow rate, and times density will be the mass flow rate or mass flux, and then times the total area, because it's the element is microscopic small, so the inlet mass flow flux will be no u dy dz much. And according to Taylor series expansion, we can write down the x component of the mass flux through the white side, okay? So that would be rho u plus its spatial derivative on x times dx. This one means the mass flux is different because its spatial derivative is not equal to 0, right? And so some go in to the control volume, some go out of the control volume, and the net width of the mass outflow through the control volume, through the control surface in x direction will be this one minus this one, right? Because this is out, this is in, and so we have this go outside, okay? Just like think about the extinguisher tank, okay? Some go out of the tank, okay? Some go out of the control volume. Not only some go out of the volume in x direction, also some go out in y direction, in z direction. And so we similarly in the next minor, we can write down the mass flux through the y direction, mass flux through the z direction. Go through the control surface. Some fluid go out of the control volume in y direction. Through the control surface, some fluid flow out of the control volume in z direction. And in total, the flow out of the CV will be x, y direction we pass it, we sum them, right? This one will be the mass flux go out of the CV in x direction. This one is because fluid flows. Some fluid go out of the CV in right direction. This one will be because the fluid flows. Some go out of the CV because in right direction, okay, through the control surface. So sure, you can write down in vector form. If you're not good at this, you can forget it. You see, some just go in, some go out. Maybe there are also mass change inside the CV. Okay, inside the CV, maybe if there is a source or if the fluid we know the fluid inside the control volume will also be different, right? The mass will also change. We can figure out this, right? Because some in, some out. So inside the CV, the mass will be different. Just now we have given examples, right? So the mass change inside the CV will be rho times its volume and take the time derivative. This will be the mass change rate inside the CV. We know mass is conserved for a system, so that means the net rate of mass flux out through the control surface plus rate of change of mass inside control volume should equal to 0. So we got this equation, okay? So this one is because inside the CV, the mass change with time. This one, these three terms is because the fluid flowing, because some fluid go into the control volume through the controllers, some go out of the control volume through this control surface or through its boundary. Okay. This one is in x direction, y direction. So dx, dy, dz cancel out. We got this equation. This one is called continuity equation. This one should be quite familiar. We have write down this before, or maybe we can write down this way. Okay, this continuity equation. Okay. For this one, we know in mathematics we can have two terms, right? And then we write down like this way. Oh, so let's say what we can write down like this way. We can do it together. Here. For this one, d rho dt plus we rho keeps rho plus rho times du dx plus u d rho dx, right? Plus rho dv dy plus v d rho dy plus rho d w dy plus w d rho dy equal to 0, right? And what's this? D rho dt plus u d rho dx plus v d rho dy plus w d rho dy. What's this? It's actually the total derivative of the density, right? This will be the total derivative of the density. Okay. Or maybe we can write down like this way. For the mass, the total mass for the system, it will be the total derivative of the mass, right? And according to the total derivative or the substantial derivative or the material derivative, it will equal to what's this? Local derivative of the mass plus what is convective derivative. U is the velocity of x velocity, this v, y velocity, right? W, dm, dz, right? And the question about this one, this is for total derivative. And n is equal to rho dx, dy, dz, right? Mass is equal to density times volume. And then you all will use rho d volume, okay? So for each term, you can use this. And later on, we will say we'll know for the dEd volume, dt is actually equal to du dx plus dv dy plus dw dz. Okay. Later on, we will introduce that. So you can derive this continuity equation from the total derivative directly, or use what we just have learned, what the net rate of mass flux out through the control surface plus rate of change of mass inside control volume will be equal to 0. So this is called continuity equation. So for this function, we can write down into different ways. We got this, for this one, we can write down like this with this total derivative, this one. For steady flow, so that means for steady flow, that means the local derivative will equal to 0. So we will get its mass flow rate. Okay, for the mass flow, for this mass flow, which the sum will equal to 0, the commutative terms. And for incompressed flow, we know incompressed flow corresponding to d0 dt equal to 0. Okay, the particle density will not change with time. And if though is a constant, so we will have the du dx. This one is actually, because some of you don't know this, du dx plus dv dy, because w dz equal to 0. So this one. Okay, so we can take 10 minutes break and then continue, okay?